Hi everyone, welcome to L.V.T Education. Today we will discuss Telangana State 10th class mathematics subject. And before starting class, could you please tell me what is meant by natural numbers? Counting numbers are called natural numbers, right? Natural numbers are indicated by n, 1, 2, 3, 4, and so on. These are called as natural numbers. Whole numbers. Next number type is whole numbers. What is meant by whole numbers? If you add 0 to the natural numbers, you will get whole numbers, right? And then integers. What is meant by integers? Negative numbers, positive numbers with 0 are called as integers. These are positive numbers, these are negative numbers, and this is 0. And then coming to these are called positive integers. These are called negative integers. If you combine 0 to the positive integers, non-negative integers. If you combine 0 to the negative integers, called as non-positive integers, right? And coming to the next number type, right? Natural numbers, whole numbers, and also integers are indicated by Z. Why do we indicate integers by Z? Because the other name for integers is Jwala numbers, right? And then coming to the next number type, quotient numbers are rational numbers, right? Rational numbers are those which can be written in the form of p by q, and q should not be equal to 0, are called as rational numbers. Ultimately, denominator should not be equal to 0, called as rational numbers. The other name for rational numbers is quotient numbers. That is why we are indicating rational numbers by q. And coming to the irrational numbers, the numbers which cannot be written in the form of q, p by q, and q should not be equal to 0, are called as irrational numbers, right? And if you combine rational numbers and irrational numbers, you will get real numbers, right? This is the chapter we are going to discuss in the 10th class mathematics subject, right? And then clear, natural numbers are counting numbers, whole numbers are, if you add 0 to the natural numbers you will get whole numbers, and Z means Jwala numbers, that is integers, right? In integers we have positive integers, negative integers, 0. If you combine 0 to the positive integer, you will get non-negative integers. If you combine 0 with the negative integers, you will get non-positive integers. And then q means quotient numbers. Quotient numbers is also called as the rational numbers. Right? Rational numbers are those which can be written in the form of p by q, and q should not be equal to 0. And irrational numbers which cannot be written in the form of p by q, and q should not be equal to 0, are called as irrational number. And I think you might have learned in your previous classes terminating decimals also. Decimals also rational numbers, right? And also non-terminating recurring decimals also rational numbers, right? Non-terminating, that means terminating decimal. My example for this one 3.5, terminating after decimal it is terminating, right? 4.6 another example. And non-terminating non-recurring means 3 plus non-terminating recurring means 3.66666 so on, 4.8888 so on, right? You might have learned this type of non-terminating recurring decimals in your 8th class also. These are also called as rational numbers. And again, non-terminating non-recurring, that means non-repeating decimals are called as irrational numbers. For suppose 3.1323456 and so on, this type of numbers are called irrational numbers, right? And these are the 9th class concepts which you have learned already in your 9th class, right? Next we will enter into the topic, and then right, okay, whenever you divide a number by another number you will get a quotient and remainder, right? Or suppose 43 divided by 7, you will get 6 times plus 1. Here this 6 is called quotient, right? This 1 is called remainder, right? This phenomenon explained by Euclid by using Euclid Division Lemma or Euclid Division Algorithm, that is A equal to BQ less R, where 0 less than or equal to R less than B, right? This is nothing but Euclid Division Lemma, right? This is nothing but division algorithm, right? Next one, and we will use this division algorithm in our first chapter, which is called real numbers, to derive to find out HCF of larger numbers and then to find out the properties of to derive the properties of real numbers, right? What is the use of this Euclid division lemma in real numbers chapter? To find out the HCF of larger numbers and derive the properties of real numbers, right? Now we will do one problem. Now we will do one problem finding HCF of two numbers by using Euclid division lemma, right? Look at here, we will find HCF of 160 by using Euclid division lemma. 60, how many times you will get? 61 times. 60 plus 40 is the remainder. This is the first step. And again in the second step, the divisor in the first step will comes as dividend to the second step, and the remainder in the first step will comes as divisor for the second step. 40 into how many times you will get? 41 time, and again you will get remainder, and the same scenario repeats here. Divisor in the second step you will get as divisor in the third step. 40 equal to remainder in the third step, you will get it as divisor, t into 2 times plus 0. This is the actual phenomenon of finding HCF of two numbers using Euclid division lemma. And then again here, what is the HCF, right? Whenever you get 0 as the remainder, in that step the divisor is nothing but HCF of the given two numbers, right? The HCF of given two numbers is 20, right? Now we will move into the concept here, and then right, look at that example 1. Show that every positive even integer is in the form of 2q, and that every positive odd integer is in the form of 2q plus 1, where q is some integer. It is a, we need to prove this derivation now. Right, we need to prove every positive integer is in the form of 2q, positive even integer is in the form of 2q, and every negative positive odd integer is in the form of 2q plus 1. Right, look at here. Let a be any positive integer and b equal to 2. Depending on the question, we will assume that b value to prove positive even integer as 2 in the form of 2q and positive odd integer in the form of 2q plus 1. Depending on the question, we will take that p value, right? By using Euclid Division Lemma, a equal to 2q plus r, where 0 less than or equal to r less than 2. Clear? What is Euclid Division Lemma? We already discussed, right? A equal to bq plus r, 0 less than r less than b. This is Euclid Division Lemma. Right, now we are using that Euclid Division Lemma to prove every positive even integer is in the form of 2q, every positive odd integer is in the form of 2q plus 1. Right, here what can be the values of r here? R can be 0 less than or equal to r less than 2. R should be less than 2. R can be equal to 0, and r can be 0 or 1. Right, now r can be 0 or 1. By looking at this, you can find out r values here. Right, now if r equal to 0, we will derive all the cases here. If r equal to 0, what is the value of a here? 2q, right? Right, what is the value of a here? 2q. Ultimately, we can say that here it is even number. A is an even number. Why? Because it is multiplying by 2, right? In the RHS side, that q is multiplying by 2, right? The numbers which are multiplying by 2, all the result gives us even numbers only, right? And then all the even numbers are present in the form of 2q. Right, next one. If r equal to 1, then a equal to 2q plus 1. Right, a equal to 2q plus 1. When r equal to 0, you will get a equal to 2q. When r equal to 1, you will get 2q plus 1. Ultimately, we can conclude that this is odd number. If you add 1 to the even number, you will get odd number. Therefore, a is an odd number. Therefore, we can conclude that every positive even integer is in the form of 2q, and every positive odd integer is in the form of 2q plus 1. And then next example, we will look into the next example. What is the next example? Look at here. Show that every positive odd integer is of the form 4q plus 1 or 4q plus 3. Look at here. This is the most important powerful terminology. Positive odd integer. Here, whenever he has given positive odd integer, we have to take a as positive odd integer, and whenever he has given as a positive even integer, we have to take that a as positive even integer, right? Here he has given, we have to show, he is asking that we have to show every positive odd integer is in the form of 4q plus 1 or 4q plus 3. That means we need to take b as 4q, right? Now we need to show every positive odd integer 4q plus 1 or 4q plus 3 forms, right? Now right, let a equal to, let a be positive odd integer. Are you getting why am I taking a be positive odd integer? In the question he has given, show that every positive odd integer is of the form of 4q plus 1 or 4q plus 3, where q is some integer, right? That is why I'm taking this as a as positive odd integer. In the previous question you may get doubt that sir, in the previous question you have taken a as positive integer, right? Positive integers either may be in the form of 2q or may be in the form of 2q plus 1. That is why I have taken a as positive integer in the previous question, right? Now I will take let a be a positive odd integer and b equal to 4. Now by using Euclid Division Lemma, a can be 4q plus r 0 less than or equal to r less than 4, where r can take the values of 0, 1, 2, 3, right? And then if we will take all the cases, if r equal to 0, a will be 4q plus 0, that equal to 4q. I can write it as 2 into 2q, right? Ultimately I can conclude that this is even number, right? In the right hand side we have two multiples are there, two multiples are even numbers. The we don't need that one, right? We need to prove every positive odd integer, right? Here we are getting even integer, right? Therefore it is not, it will not need us, right? Next, if r equal to 1, right, a can be, right, 4q plus, in the place of r we will substitute 1, that equal to 4q plus 1 can be written as 2 into 2q plus 1. Look at here, it is 2 multiple plus 1. When you add 1 plus when you add 1 to 2 multiple, you will get odd number, right? We can conclude that it is odd number, right? Next we will do it. we'll look into the next question. If r equal to 2, r will equal to 2, 4q plus in the place of r we will substitute 2, that you will get, if you take 2 as common, 2q plus 1. This is completely 2 multiple. Ultimately we can conclude this as even number, right? Therefore we will go for the r equal to 3. If r equal to 3, therefore a equal to 4q plus 3. I can write it as 2 into 2q plus 2 plus 1, 2 into 2q plus 1. If I take 2 as common from these two terms, you will get, right? This is 2 multiple plus 1. When you add 1 to 2 multiple, when you add 1 to 2 multiple, you will get odd number, right? It is odd number. Therefore I can conclude that what are the odd numbers here? When you got 4q plus 1 and 4q plus 3, that numbers we have concluded as odd numbers, right? Therefore we can conclude that every positive odd integer is in the form of 4q plus 1 or 4q plus 3. Right now we will move into the exercise. Right, this is our conclusion. Right, and the next exercise is, right, this is our conclusion. We have concluded that question now, and the next one, we need to complete exercise 1.1. You use Euclid algorithm to find HCF of, right, first question, second question, and third question. We will discuss first question now. 900 and 270, right? 900 comma 270, right? I will take large number in the left hand side. 270, how many times? You will get 273 times 8, 10. That's what is the remainder now? 90. And in the second step, the divisor in the first step will comes to divide into positions. 270, and we will get 90 into 3 plus 0 is the remainder. In this case we got 0 as the remainder in the second step only, where you will get 0 as the remainder. 9, the divisor in that step is nothing but HCF of the two numbers, right? HCF of 900 and 270 is 90. And then you can do rest of the questions, rest of the two questions. And coming to the next question, use division algorithm to show any positive odd integer is in the form of 6q plus 1 or 6q plus 3 or 6q plus 5, where q, right? Same, we will go same procedure, right? Second question, let, there he has given positive odd integers, right? Let a be any positive odd integer. Let a be any positive odd integer, and there he has asked to find out, he has asked to show every positive odd integer is in the form of 6q plus 1 or 6q plus 3 or 6q plus 5, right? I will take b as 6. Then by Euclid Division Lemma, a equal to bq plus r 0 less than or equal to r less than 0 less than or equal to r less than b, we will get a equal to 6q plus r, 0 less than or equal to r less than 6. Right here r can take 0, 1, 2, 3, 4, 5. Right here r can take the values of 0, 1, 2, 3, 4, 5. Right. If r equal to 0, a will be 6q, that I can write as 2 into 3q, right? It is even number. We have discussed this type of numbers previously. Why? Because 2 multiples are even numbers. If r equal to 1, a can be 6q plus 1. Right? Can I write it as 2 into 3q plus 1? I can conclude this as odd number. Why? Because 2 multiple plus 1. Odd number. Look at here, 6q plus 1 is odd number. If r equal to 2, that implies a can be 6q plus 2. I will write it as 2 into 3q plus 1. If I take 2 as common here, again it will become even number, right? Because it looks like as 2 multiple, right? It is even number. But we need to look into the odd numbers only. If r equal to 3, that implies a equal to 6q plus 3. I can write it as 6q plus 2 plus 1. I can write it as 2. If I take 2 as common, 3q plus 1 plus 1. I can conclude that this is odd number. Right? Because 2 multiple plus 1. Right now, I need to check another 2. R equal to 4. That implies a equal to 6q plus 4. Right? Here, I can write it as directly, if I take 2 as common, 3q plus 2. It is directly I can conclude that it is even number, right? Because it looks like as 2 multiple, right? Even number. Right. If r equal to 5, a can be 6q plus 5. I can write it as 6q plus 4 plus 1. I can simplify if I take 2 as common here, 3q plus 2 plus 1. Anyway, it is 2 multiple plus 1. 2 multiples are even numbers. If you add 1 to the even numbers, you will get odd numbers. Look at here, observe here. When r equal to 1, you got when r equal to 1, you got an odd number, right? When r equal to 3, you got odd number. When r equal to 5, you got odd number. Then you can conclude that every positive odd integer is in the form of 6q plus 1 or 6q plus 3 or 6q plus 5. This is our conclusion for this question. And coming to the next question. What is that next question in your textbook? Use division algorithm to show that the square of any positive integer, he did not mention any positive odd integer or even integer. He mentioned only positive integer. We have to take a as positive integer now, right? Is of the form 3p or 3p plus 1 right now. Look at here. What is the question number? 3, right? Right, 3. Now let a be positive integer and b equal to 3. Why? Because there he has taken b, right? Look at here, every positive square integer square should be is in the form of 3p or 3p plus 1. Look at here, that is why I have taken b as 3, right? Now by Euclid Division Lemma, a equal to bq plus r, where 0 less than or equal to r less than b, we will get a equal to 3q plus r, where 0 less than or equal to r less than 3. Right here, r can be 0, r 1, r 2. Why? Because r should be less than 3, greater than or equal to 0, right? R can be 0, r1, r2, right? Whenever if you take r equal to 0, that implies a can be a equal to 3q, right? Squaring on both sides. Why do we do squaring here? Because we need to show every positive integer is in square of every positive integer is in the form of 3q or in the form of 3p or 3p plus 1, right? Squaring on both sides right now. If you do squaring on both sides, a square equal to 9q square, right? I can write it as 3 into 3q square. Only square is for q, right? I'm assuming this 3q square as p, right? This 3q square as p, and therefore square of the positive integer is in the form of 3p, right? Where p equal to 3q square. And again we'll move to the if r equal to 1. If r equal to 1, a can be a equal to 3q plus 1. Again squaring on both sides, we will get a square equal to 3q plus 1 whole square, and a square can be a plus b whole square, a square plus b square plus 2ab, 9q square plus 1 plus 2ab, 2 into 6q, right? Can I write it as, if I take 3 as common, 3 into 3q square plus 2q plus 1. Can I write this as 3p plus 1, where p equal to 3q square plus 2q. But again I got another result. Square of positive integers is in the form of 3p plus 1, where p equal to 3q square plus 2q. Again I will check r equal to, we have r values 3, 0, 1, 2, right? Right, look at here, a equal to 3q plus 2, squaring on both sides, that gives us 3q plus 2 whole square, right? If you simplify this one, 9q square plus 4 plus 2, 3 is 6, 2 is 12q, right? I can simplify this as 9q square plus 3 plus 1 plus 12q. If I take 3 as common from all the terms, you will get 3q square plus 1, you will not get common from 1, plus 4q plus 1. This can be written as 3p plus 1, where p equal to here, where p equal to, you will get anything as p, but it is in the form of 3p plus 1, that's it. 1 plus 4q. It is also in the form of 3p plus 1. In the second case, when r equal to 2, you got 3p plus 1. In the first case, only in the form of 3p. Therefore, every positive integer, square of every positive integer, we are getting the forms of 3p or 3p plus 1. Therefore, I can conclude that square of every positive integer is in the form of 3p or 3p plus 1, right? This is the third question, I think. And coming to the fourth question, by using a division algorithm, show that cube of any positive integer. Look at here also same thing, positive integer, but here we have 9m or 9m plus 1, 9m, 9m plus 1 or 9m plus 8. Look at here we will not take b as 9. Why? Because if you take b as 9, you will get r values from 0 to 1, 0 to 8, right? That is why we are taking r value as 3. Why? Because let a be any positive integer, let a be any positive integer, and r equal to 3, because 3 is also the factor of 9, right? You will get same forms, but don't take for all the numbers. Why? Because it takes more time to simplify all the values from 0 to 8. That is why I'm taking r equal to, sorry, b equal to 3 here, not r equal to 3, b equal to 3, because 3 is also the factor of 9, right? Done. Look at here, let a be any positive integer, b equal to 3. By Euclid Division Lemma, by Euclid Division Lemma, a equal to bq plus r, where 0 less than r less than b, you will get a is equal to 3q plus r, where 0 less than r equal to r less than 3, where r can take the values of 0 or 1 or 2. Did you get it? Why am I taking here b equal to 3? Because if you take r equal to 9, you have to simplify r equal to 0, r equal to 1, r equal to, and so on, up to r equal to 8. That is why I'm taking b equal to 3, because 3 is also a factor of r. 3 is also a factor of 9. Right now, equal to, if r equal to 0, a equal to 3q, we will get a equal to 3q, right? That implies we need to find out the cube of every positive integer, right? cube, a cube equal to 3q whole cube. Can I write this as 27q cube? Can I take here 9 common? You will get 3q cube. I can write it as 9m, right, where m equal to 3q cube, right? We got positive integer is present in the form of 9m, whether irrespective of m value. M can be anything, right? Next one, if r equal to 1, that implies a equal to 3 cube plus 1. Here we need to find out cubing on both sides. Here also cubing on both sides. I might have forgotten that here. Here also same, cubing on both sides. You will get right. You will get a cube is equal to 3 cube plus 1 whole cube. Right. It is in the form of a plus b whole cube. We know a plus b whole cube equal to a cube plus b cube plus 3ab into a plus b, right? I can simplify this as a cube means 3q whole cube, 27q cube, b cube means 1 plus 3ab, 3 into 3q into 1 plus a plus b, 3q plus 1. This is a simplified form of this 3q plus 1 whole cube. Right now, again, I will write by rearranging the terms, plus 3 3s are 9q into 1 9q only, plus 1 plus 1. Again, if I take 9 as common from these terms, these two terms, right, you will get, if I take 9 as common, 9 3s are 27 q cube plus, already 9 come outside, 9 1s are 9, you will left with q, 3q plus 1 plus 1. I can arrange this as, I can indicate this as 9m plus 1, right, where m equal to 3q cube plus q into 3q plus 1, right, 3q plus 1, right? Therefore, I can conclude that cube of any positive integer is in the form of 9m plus 1. And again, I need to check r equal to 2, right? I need to check r equal to 2. Then when r equal to 2, if r equal to 2, a can be 3q plus 2. Again, we need to do cubing on both sides. Cubing on both sides, you will get a cube equal to 3q plus 2 whole cube. We have already simplified that as a cube plus b cube plus 3ab into a plus b. Formula, we know the formula, right? I'm simplifying directly there. A cube plus b cube plus 3ab, 3 into 3q as a into 2a plus b, 3q plus 2, right? This I can simplify as 27q cube plus 2 cube as 8 plus 3 3 is a 9, 9 2 is a 18. I will write it as 9 into 2q only. Multiplication is commutative, right? 3 3 is a 9, 2 into 2q, 3q plus 2. I will arrange these terms again. 27q q cube plus 9 into 2q 3q plus 1 plus 8. Can I take 9 as common from these two terms? If I take 9 as common from these two terms, 9 3s are 27, q cube 9 come already outside. I will left with a 2q into 3q plus 2, right? And 8. I can conclude this is in the form of 9m plus 8. Either it may be anything, right? It may be anything. I can write it as 9m plus 8. Now I can conclude that therefore cube of every positive integer is in the form of cube of every positive integer is in the form of 9m plus 1 or 9m plus 8, right? This is our conclusion. And then coming to the next question, show that one and only out of n plus 2 n plus 4 divisible by 3. But depending on the 3, we will take b value here, where n is any positive integer, right? N is, right, between right, n means a only positive integer, right? Here we will assume n as a here, right? I will move into the concept. We have proved fourth question also, right? Next one, fifth one, right? Look at here. If let n be a positive integer and b equal to 3, we need to prove from n plus 2 or n plus 4 any one of those among those three terms divided by 3, right? Now by using Euclid Division Lemma, a equal to bq plus r, where 0 less than or less than b. Here in the place of a we have taken n, in the place of b we have taken 3, q plus r, 0 less than or equal to r less than 3, where r can take the values of 0, r1, r2, right? Now if r equal to 0, that implies n will become 3q, right? N will become 3q. It is 3 multiple, right? 3q means 3 multiplied by something, 3 multiple, right? It is 3 multiple, that means divisible by 3. It is divisible by 3. And again we need to check n plus 2, n plus 4 in the case of r equal 0 only. In the case of r equal 0, we need to check n plus 2, n plus 4, right? I will take now n plus 2. If you add 2 on both sides, you will get n plus 2 in the left hand side, 3q plus 2 in the right hand side. It is not divisible by 3. Why? Because 3 multiple plus 2 will not give 3 multiple, right? Then it is not divisible by 3, right? Next one, n, if you add 4 to the left hand side and right hand side of n, you will get n plus 4 here, you will get 3q plus 4. You can write it as 3q plus 3 plus 1. You can write it as, if you take 3 as common, 3q plus 1 plus 1. 3 multiple plus 1 will not give us, give us 3 multiple, right? Therefore it is also not divisible by 3, right? And again, if we take r equal to 1, if you take r equal to 1, look at and understand here, we need to know Euclid division lemma, and then we will prove all these problems by using the Euclid division lemma only, right? If r equal to 1, if r equal to 1, n will become 3q plus 1. It is 3 multiple plus 1. It is not divisible by 3. It is not divisible by 3. When you add to second case, right, on both sides, you will get 3q plus 1 plus 2. This can be written as 3q plus 3. If you take 3 as common, q plus 1. It is 3 multiple, right? Therefore, we can conclude that it is divisible by 3. And if you add 4 to the left hand side and right hand side of n, where in the case of r equal to 1, you will get 3q plus 4, and 3q plus 1 plus 4 here. 3q plus 1 plus 4. This can be written as 3q plus 3 plus 2. This I can write it as 3 as common, 3q plus 1 plus 2. 3 multiple plus 2 will not gives us 3 multiple, right? Therefore, it will also not divisible by 3. Right, among these 3, n plus 2, n plus 4, only 1, that is n plus 2, is divisible by 3. And again, if you check for n plus, if r equal to 2, right, if r equal to 2, if you check if r equal to 2, Euclid division lemma, n equal to 3q plus 2, right, n equal to 3q plus 2. And then again, here it is 3 multiple plus 2. It will not be divisible by 3, right? 3 multiple plus 2 will not give us 3 multiple. And again, if you add 2 on both sides, you will get 3q plus 2 plus 2. You will get 3q plus 4. That gives us 3q plus 3 plus 1. That can be written as, if you take 3 as common, 3q plus 1 plus 1. 3 multiple plus 1 will not gives us 3 multiple, right? 3 multiple next number will not gives us 3 multiple. And again, if you add 4 to the left hand side and right hand side of n when r equal to 2, you will get 3q plus 2 plus 4, right? You can write it as 3q plus 6, right? If you take 3 as common, right, it is 3 multiple, right? Ultimately it is 3 multiple, then it is divisible by 3. Look at here, in 3 cases, only one of among 3, only one among, in the first case, n value divisible by 3. In the second case, n plus 2 is divisible by 3. In the third case, n plus 4 divisible by 3. Therefore, we can conclude that only among n plus 2, n plus 4 is divisible by 3. Therefore, only one among n comma n plus 2 comma n plus 4 divisible by 3, where n is a positive integer. integer. Right? With this we have completed first exercise, and regarding first exercise I can say that a equal to bq plus r, where 0 less than or equal to r less than b. Why do we take that is called as Euclid Division Lemma? Why do we take that Euclid Division Lemma in real numbers? That is useful to find out HCF of larger numbers, and also to prove some properties, to prove some properties of the real numbers. Right? We have done that we have proved that properties of real number, and